All right, welcome back. Today we're going to talk about buoyancy, and you've probably always have dealt with this when you go swimming with a beach ball underwater. Like you try to push it, the farther down you go, the harder and harder, and then it pops right up to the top. All right. What happens is there is a pressure distribution around that ball, and we know that pressure gets higher as it goes downward. Okay. So that pressure distribution in that water creates this buoyancy force. Okay. So if we look at, so say here's a free surface, top of the water, and say you have some shape or the ball. Okay. When we look at the pressure distribution, it should get bigger and bigger and bigger. Okay, and it should kind of follow the shape, but that's okay. Right? The pressure distribution below it is higher. And typically with a beach ball, right, it's enclosed and there's air inside, and that air is a lot lighter, right, than the surrounding liquid. Okay, so you, again, creates that pressure distribution. All right. So what we have, and we have buoyancy force even in air with but it's so small because the air density is so small that it's so the buoyancy force is so small. So you have buoyancy force, and then you have weight, and it acts in this case at the centroid of the displaced volume. Okay, so we know that the weight is mass times gravity, and that's the density of the body, and I'll put these times gravity times the volume total, where the density of B is the density of the object. Okay. V total is the total volume of object. Okay. Where now the buoyancy force I put that on silent, I'm sorry, would be the density of the fluid times gravity times the volume submerged. Okay. Where density of F is the density of the fluid, and V sub is your submerged volume. Okay. And in this case, because it's completely down, V sub would be like the total volume. However, like if you have an ice cube, and we'll do a problem, not all of it's submerged because it floats. Okay. So let's do a practice problem. Here is a practice problem. We have, I'm going to do a sketch over here. And, I'm going to do blue here because we're going to be in water. So here is the top of the water. It's too thick there. Let's do this. Here's a cable. Here's a balloon or a buoy. Okay. Let me make that circle bigger. Type buoy. So we have a buoy anchored on a cable. Okay. Or, yeah, that's good. We have sea water here. And givens. What do we have for givens? The diameter of that buoy is 1.5 meters. The weight is 8.5 kilonewtons for that. And gamma of the seawater is 10.1 kilonewtons per meter cubed. . And what we're going to find is the tension in that cable. Okay. So I'm going to do a free body diagram right here. Let's make it purple. Free body diagram. So here is the buoy. Okay. We have the buoyancy force. We have weight. And then we also have the tension from the cable. Okay. All right. Solution. Newton's second law. Well, sum of the forces, let's call this the z direction, and let's go upward. Z equals 0. We'll make upward positive. We have force of buoyancy minus weight minus the tension equals 0. The tension would equal the buoyancy minus the weight. Tension, the buoyancy force, we know is the density of the fluid times gravity times the volume submerged. And this actually becomes gamma, right? Because rho g is gamma times volume submerged. And the volume submerged is pi d cubed over 6 because it's a sphere. Let me fix that. Let me just call this the buoyancy force. Okay. And then the weight, I believe we have, right? Yep. Okay. So now the tension becomes gamma pi d cubed over 6 minus the weight. And the tension now becomes, what was gamma? 10.1 kilonewtons over meter cubed times pi times 1.5 meters cubed over 6 minus 10.1 kilonewtons over meter cubed. Oh, no, that's the W. Sorry. That was gamma. W was 8.5 kilonewtons. So the tension becomes 9.35 kilonewtons. So we used buoyancy force, we used the weight force, we had a tension in the cable, so we could find the tension. All right, I'll have another video on another example. Take a look for that.